This video is about statistical process control, or SPC. SPC can be visualized as a cycle. Each iteration of the cycle begins with assessing or reassessing goals of the process being monitored. Such goals could include a baseline for product quality or a ceiling for how much waste is produced. Then, data is collected and usually stored in a control chart, which is used to identify assignable variations in the process. Control charts only confirm the existence of variations. They do not identify what is the exact cause. More data is to be collected to isolate where in the process a variation might spawn from. After the existence of assignable variations is confirmed, the next step is to eliminate them. An important note is that SPC is a continuous process. Data is constantly collected to improve and update the types of variations evident in the process. The end goal is to reach stability, where only natural causes of variations remain. There are two predominant types of variations: special or assignable variations such as operator error and machine wear, and common or natural variations such as power outages, weather changes, and traffic. Unlike common variations, special variations can be found and eliminated from the system. When special causes of variations are removed, only predictable variations remain. Such a process is then said to be stable. Control charts tell us whether or not a system is in a state of control or stability. These charts portray this information by plotting some statistics such as mean solder application over some time period. A central line that represents the mean of the statistic is drawn to show how an instance of the process compares to the average. Upper and lower boundaries are shown on a control chart to show the extremities, usually in terms of 3 standard deviations. When data goes beyond or approaches these boundaries, an engineer conducting quality control can conclude the existence of a new or current variation in the process. As you can see, this control chart portrays the varying amount of solder application by an experimental soldering machine. The y-axis represents solder application in micrograms, and the x-axis represents the days of use of the machine. The central limit represents the mean of the application of solder over a span of 15 production days. A computer engineer that is in charge of calibrating this new machine can use this control chart to see which days have a more controlled application of solder that fits along the mean control limit, which could help the computer engineer determine which settings for the machine calibration are best. The computer engineer can observe patterns of the data that approach the upper and lower control limits to determine whether or not there is some sort of assignable variation in the process that can be identified and then eliminated. By utilizing this control chart and continuously adding data to it, not only can the engineers working with the machine maximize application efficiency, but they can also reduce over-application of the solder. To conclude, SPC is a useful tool for all engineers. By continuously collecting data, engineers can remove assignable variations in order to improve the quality of a process or system.